Math 1343, Week 8, Video 10, Calculating the Test Statistic for a Test for Association. Well, so far in the previous two videos, we've stated what a test for association is and how to state the hypotheses for it. Just a reminder, in a test for association, the null hypothesis in general is there is not an association between these two categories, whereas the alternative hypothesis is there is an association between the two categories. And in the previous video, we eventually figured out how to calculate our expected values based on our observed values using the column and row and grand totals from the observed values and this formula for calculating the expected value for each cell by multiplying for a given cell the row total times the column total divided by the grand total, none of which totals are written here. I've simply copied the observed values and expected values. But in the context of hypothesis testing, our move is to come up with some measurement that compares what we observed versus what we expected so that we can pass judgment on the null hypothesis. If what we observed and what we expected don't differ by too much, then we say that the discrepancy is based on the sample selected, not the fact that the null hypothesis is wrong. But if what we observed deviates too much from what we expected, then we don't blame it on the sample. We say our null hypothesis was wrong to begin with. So in order to make that determination, we have to calculate the test statistic. So how are we going to calculate the test statistic that measures the difference between the observed values and the expected values? The answer is in a formula that we've already seen. The formula for the test statistic for a test for association is, well, first off, this will be a chi-square distribution. And by the way, the criteria for the chi-square distribution being appropriate for this is every expected value should be at least 5. Same as the criteria for using a chi-square distribution for a goodness of fit test. Clearly, our expected values are all at least 5. But the formula for the test statistic for a test for association is the exact same as the one for a goodness of fit test. It's the sum of the ratios of the squared difference between the observed value and expected value compared to the expected value. And we run this sum over each different cell. In this case, we have 6 cells to run it over because each contingency table is a 2x3 table and has 6 cells. So it's the same formula as before. And it's going to get messy. So let's jump into it. For this one, I will do the male column first and then the female column second. So let's start with the male column. In the male column, what we observed for male bachelor's degree was 1,340 minus what we expected was 2,018. Now that's a pretty large difference and it's going to get squared. But it's going to get compared to what we expected, which was 2018. So maybe dividing it by 2018 won't let it get too out of control. And again, this is for male bachelors. If we continue doing these cells for the males, then the number of males that we observed who got master's degree was 4,110 minus what we expected was 4,369. That difference gets squared. And then that gets compared to what we expected, which was 4,369. This is male masters. And then, same thing for male doctorate, 17,383 is what we observed, minus what we expected was 16,446, squared, and then that gets compared to what we expected, 16,446. So this is male doctorate. It's not necessary to label the cell that each fraction came from. That's for instructional purposes. But now I have to do the same thing for the female cells, for the female column, and I hope it will fit in the space that we have here. I'll make it work. Let's go ahead and set that up. All right, so moving to the females, female bachelor. What we observed was 2,899 minus what we expected was 2,221. That difference is squared and gets compared to what we expected, 2,221. For females who receive master's degrees, what we observed was 5,067 minus what we expected was 4,808. That difference will get squared and compared to 4,808, compared to what we expected. And then finally, for females who received a doctorate degree, I'm going to make this fit in this area over here. We observed 17,161 females. We expected 18,098. That difference gets squared and compared to what we expected, which was 18,098. So as you can tell, it's a pretty monstrous setup. And this is actually a small contingency table. This was just a 2x3, which had 6 cells, therefore 6 fractions. Imagine if we had a 5x5 table with 25 cells. Needless to say, as the tables get larger, you should relegate the work to technology. Microsoft Excel can do this really quickly if you know how to ask it. But I'm not going to require everybody to use Excel. I do want everybody to use the technology they're comfortable with. At the very minimum, a calculator. All right, so what's the best way to put this in a calculator? Cautiously and slowly. What might help is to calculate each numerator separately. And then that way you can just do plus and divide all the way across. It's not impossible to type the whole thing in one fell swoop. It's just such a lengthy calculation that there's a tendency to make errors, which makes sense. The more keys you press, the more chance you have of pressing one incorrectly. But at the same time, you don't want to do exactly one calculation at a time, because then it'll take you forever. So I think the compromise to streamline the process is to calculate the numerators first, rewrite the expression, and then finish it off. 1340, and it's easy to do without parentheses. You just got to complete the subtraction before you square. So I'm going to call out what I'm pressing. With the first numerator, 1340 minus 2018 equals, and then square that to get, oh hello, 459,000, that's not right, is it? I guess so. 459,684. You don't know this yet, but at this point the hypothesis test is practically over. And the next one, if we subtract 4,110 minus 4,369 and square that difference, we get 67,081. On the next fraction, if we subtract 17,383 minus 16,446 equals and square that, we get 877,969. In the fourth fraction, if we subtract 2,899 minus 2,221 and square that difference, we get 459,684. And you might be thinking, isn't that the same as this number? And is that a coincidence? The answer is yes, and not necessarily. But let's not dwell on it too much. I wonder if it'll happen again though. Fifth fraction, 5,067 minus 4,808 equals, and if we square that, we're going to get 67,081, which does match that, and it's not really a coincidence. If one of your dimensions is only 2, this is a 2 by 3, then you typically get some repeated numerators like this. I'm not going to get into the theoretical reasons why, but in the last one, I'm going to predict that it's this number, 17,161 minus 18,098 equals, and we square that, and guess what we get? 877,969. Again, the fact that these numerators occurred in 3 pairs of matching numbers is not necessarily a coincidence, but I wouldn't read too much into that. All right, so now we just got to put all that in there. What a lengthy problem. 459,684 divided by 2018 plus 67,081 divided by 4,369 plus 877,969 divided by 16,446 plus 459,684 divided by 2,221 plus 67,081 divided by 4,808 plus 877,969 divided by 18,098 for a grand total, and we'll round this to 4 decimal places, 565.9662. Now this is assuming I didn't make any calculator errors. I'm not going to waste your time going back to review it. If I did make an error, I'm sure somebody will point it out in the comments of this video, at which point I'll put a correction in the description of the video. So is it a lengthy calculation? Yes. Does it always get this crazy? Not really. This just happened to get crazy because I used real world data, which is often 4 and 5 digit numbers. And this table had 6 cells, which meant 6 fractions. But the key thing about calculating the test statistic, once you have the expected values, is we're using the exact same formula that we used for the test statistic for a goodness of fit test. We just have to set up this fraction one time for each cell. And then painstakingly, or using technology, push your way all the way through it until you get the test statistic.